Hey guys, and welcome back. So yesterday we talked about how an atom of an element can decay into the atom of another element. And today we're going to continue talking about nuclear chemistry, and we're going to learn the difference between fusion and fission, which will likely be a review from Earth Science. And then we are going to talk about how to calculate half-life, which we will have to do on our test, and then of course our midterm and our final. So let's go ahead and jump in. So I'm going to skip over this just because you guys will do this in the engage portion of your lesson today. All right, so today we're going to talk about fusion versus fission. Now, fusion and fission are a part of nuclear chemistry because it has to do, again, with the nucleus of the atom. So what's going on with our protons and our neutrons in the middle. Now, fusion means joining two things to create a single entity or two or more things. Okay, so fusion is a natural process. If you guys remember from Earth Science, when we talk about radiation in our stars, fusion takes place when a small nuclei join to make a larger nuclei. So when this happens, a large amount of energy is released. And again, this is occurring naturally in stars like our sun. So we all know we get energy from the sun. It comes in the form of radiation. The plants love it. They take it in. They do photosynthesis with that energy. That energy is coming from the fusion that's happening inside the sun. So these nuclei are coming together to form the heavier nuclei, and then they're kicking off the energy. It usually occurs in atoms that are smaller than iron. So specifically in space, we're talking about like hydrogen and helium. So those very lightweight elements. Fission, on the other hand, is the opposite. So we're splitting a larger atom into smaller parts. Now, fission is when we break the atom down, and just like in fusion, when we do fission, we're also releasing a large amount of energy, okay? Particularly in fission, this is when an unstable atom is bombarded with neutrons, okay? So we're using neutrons, we're throwing it at the nucleus, and then it's breaking into smaller parts. Again, an incredible amount of energy is released, and this can then be converted to electricity. This is going to happen in atoms that are typically larger than iron, and for us, we are using uranium. So fission is man-made. This does not happen naturally because it takes a large amount of energy and manipulation in order to split an atom. This is where things like our nuclear weapons come from, right? So when we're talking about wartime and the creation of weapons of mass destruction, that's fission. That's nuclear chemistry. We're breaking these atoms apart, releasing a large amount of energy. Now, when it's controlled, it can be used to create electricity. So in nuclear power plants, we use the neutrons. We bombard uranium with the neutron. It breaks the atom apart, which releases the energy. Now, that energy creates heat, which then we use to heat up water, which creates steam, which then turns a turbine, which then gives us our electricity. Now, people can be kind of apprehensive about nuclear energy, but it's actually a pretty clean source of energy. It doesn't release any kind of carbon dioxide into the atmosphere, but the issue is that there is some radioactive material that's left over, and right now we don't really have a great way to dispose of it. What we do is we put it in lead-lined barrels and we kind of just bury it in the desert. So, but it is a good way to generate electricity. So neutrons are emitted through fission, which can lead to a chain reaction. Again, this is what's used in atomic bonds. So when you're breaking the atom apart, you're releasing more neutrons from the nucleus of the atom, which can then go on to bombard other atoms and break them apart as well. And that is what we do in nuclear reactors. All right, so really quickly, remember we have three different types of radioactive decay. We have alpha decay, where our nucleus loses an atomic mass of 4, and then we lose 2 protons, so we're kicking off that helium nucleus. Beta decay, where a neutron turns into a proton, where we're adding 1 to our atomic number. And then we have our gamma radiation, where we're just losing energy from the nucleus and nothing changes. So our element doesn't change with gamma radiation, we're just losing a large amount of energy. So those are our 3 types of radioactive decay. Now, we know that in nature, unstable isotopes decay spontaneously. So remember, an isotope is a variant of an atom, right? So if it's unstable, it will decay spontaneously, which means it will decay into a different element. And it doesn't take any human intervention to do that. But how long does it take to get to that point? So let's say that an unstable atom starts to decay into a stable form of a different element. How long is that process going to take? Well, the answer is it depends. It depends on the actual element itself, but we can calculate the half-life of our elements and we can figure out how long it will take. And that is this concept called half-life, which we're going to learn how to calculate today. So half-life is the average amount of time it takes for a radioactive substance to decay half of its original mass, okay? So if you start with like 10 grams of a substance, how long does it take to decay into 5 grams? How long does that 5 grams take to decay into 2.5 grams? How long does 2.5 grams take to decay into 1.25, okay? Now, we can figure out half-life 2 ways. Half of it is to graph it. So we have our number of half-lives and our percent isotope remaining. So on our x-axis, we would graph the half-lives, so how many there are, and then the percent isotope remaining. Now, a half-life is just the amount of time it takes. So a half-life event is the substance decaying to half of its original amount. So going from 10 to 5, that's one half-life event. Then that same sample goes from 5 to 2.5, that's another half-life event, okay? And the percent of the isotope remaining, that's the percent of the whole, so the original that we start with. And here is an example of how we can graph it. So it doesn't tell us what this element is just because it's just a typical graph. So we start with 100%, okay? Then we have one half-life event. In this particular example, a half-life is 5 years because we go from 5 to 10 to 15 to 20. So we're going up by 5 years. So the time of the half-life itself is 5 years. But each of these is one half-life event. So one half-life event is 5 years. So here's half-life event 1, half-life event 2, half-life event 3, 4, and 5. And then, of course, each time, because it's a half-life, we're going down by 50%. So we start at 100, 50%, 25, 12.5, 6.25, and then to 0, okay? It can get tricky when we're talking about the half-lives versus the decay of the sample. And I'm going to show you guys where students can get tripped up a lot of times on the next slide, okay? So when we're trying to figure out half-life, the best thing we can do is use a table to help us. So of course we're going to use a calculator if it's a larger sample size, but a table can really help us figure it out. So we're going to create a T-chart, and this is the steps to do that. We're going to label one side time and the other side amount. So here's my table. I'm going to have my time on the left-hand side, so this will be my half-lives, and then I'm going to have my amount of my sample on the right-hand side. The initial start time is always 0, okay? Because we're starting with 100% of our sample, and our 0 is our initial time, because we're always starting at 0. For every time interval, we're going to divide each amount by 2, because it's being halved. Okay? And that's it. Sorry, I thought there was one more. So, label time and amount starting at 0, so we'll always put a 0 here, and we'll always put the amount that we start with. Then on the left-hand side, you're going to go up by the half-life, so the time of the half-life. So in that last example, it was 5, so you would do 5, 10, 15, 20, 25, and then the amount would get halved on each side. So I'm going to show you an example and what this chart would look like, okay? So cobalt-60 has a half-life of 5.27 years. How much of a 10-gram sample will remain after 21.08 years? So let's go ahead and use our chart to help us figure this out. So we know our initial amount is 10 grams and our half-life is 5.27 years. So let's set up our table. Now, remember I told you we always start with 0 for our time because this is our initial. We're starting from the beginning, right? In the beginning, we had this much of the sample. And on the right-hand side for our amount, we're going to start with our initial amount, which is 10 grams, okay? Now, for every column in the left-hand side, or for every row, we're going to add the amount of the half-life. Okay, so we're going to add the half-life on the left. And on the right, for our sample, because it's decaying, we're going to divide by 2. Excuse me. So on our left-hand side, we have 5.27 years. This is one half-life event. So from 0 to 5.27, we've got one half-life event. And here we're going to do 10 divided by 2. So that gives us 5 grams. Next up, we're going to go add another half-life event. So this is half-life event 1. Now we need another one. So we're going to add 5.27 years, which will give us 10.54 years. Okay. On the right-hand side, divide by 2. 5 divided by 2 is 2.5. Okay. Now, up until this point, most students don't have any issues. Okay, because they're like, yeah, we're adding our half-lives and we're dividing by 2 on the right. This is where students make mistakes. So please listen. At this point in time, what a lot of us want to do, and I'll admit I make mistakes sometimes and it's natural to want to do it. At this time, students will want to double this number. Okay, so if you were working ahead and you were like, oh yeah, it's going to be 21 point so-and-so. No. The half-life event is 5.27. You are adding in this category. You are not multiplying by 2. You're adding. Because we're adding here, this one, yes, is doubled, but you added 5.27 to 5.27. That's why it's doubled. You're adding 5.27 to each of these columns. Okay, or rows, I should say. So it's not doubling. We're not going to do 10.54 plus 10.54. The half-life is 5.27 years. So we're going to add 5.27, okay? So it's 15.81. And that is, I've taught chemistry now lots of times. And each time I do half-life, that's always the mistake I see here. All right. Now on the right-hand side, we're still divided by 2. That one's easy. So 1.25. Now, we're not going to add 15.81. We're adding 5.27 because the half-life is still 5.27 years. It's still going to take 5.27 years for that amount to decay. So here we have 0.625 grams, okay? Now, here's our answer because it asks us how much of the 10-gram sample will remain after 21.08 years. Well, here we're at 21.08 and we have 0.625 grams left. So that is your answer, okay? So just be sure when you are working these out, drawing your T-charts, you can do this in like Google Docs. If you just pull up Google Docs and make a 2 columns table, super easy to do that. You can do it in Excel or you can do it on paper. Either way, as long as you come up with the right answer, you're good. Now, there will be some examples where maybe you have to work backwards, where it'll give you an amount and how many half-life events it takes, but it's just you're still using the T-chart, right? So we know on the left-hand side, these are the half-lives. Each one of these is a half-life event. So like from 0 to 5.27, that's half-life event 1. So we would have 1, 2, 3, 4 half-life events here. So like if there was a question that says, how many half-life events would it take to get to 0.625 grams? The answer would be 4 because it took us 4 half-lives to get there. Okay, and in that instance, you just count the jumps between the half-lives. Okay. All right, so we're definitely going to do more examples of these in our independent practice today, but that is the rundown of half-life. If you guys have questions, of course, let me know, and if not, I will catch you next week, or in the next lesson, I should say. All right, bye guys.